Hello everyone. I'm sorry I had to be gone, but I know you'll be in good hands when I get back. If you would please start by having out last night's assignment. Yesterday we began to investigate how to graph exponential functions. We looked at exponential growth functions, and the answers to that are right here. I'll just read them off, and then if you need to, when I'm done reading it off, our guest teacher could pause the video if anybody else needs to see them. Again, these are just sketches, so their exactness is going to be a little tough. Even some of them were decimals. To plot those can be tough. So mostly you're just looking at the basic shape of the graph and trying to connect some interplay between those. So first one was given a set of data. Can you write the exponential equation for it? First one was y equals 1 times 11 to the power of x. Your y-intercept is 1 and the pattern is multiply by 11. The second one, it's y equals 1/4 times 2 to the power of x. Your y-intercept was 1/4, and the pattern in that table was multiply by 2. Third one was, it looks like a steep exponential growth. In the fourth one, a more moderate exponential growth. So the rest of these I'll kind of leave up. If anybody has specific questions, you can ask them when I get back. But again, we're just looking at making tables. You can make tables by hand, or you could use the calculator, type in the equation, and then hit the second table key to get a table and just plot points. So you're just looking at general shapes. The one I would like you to kind of look at, I believe, were the last ones, like 12, 13, and 14. There was some interconnection between those, so see if you can note how those are similar and how those are different, and we'll go over that more when I get back. So if we need to, you can pause the video now so people can correct their homework. If this is good, then we can just kind of continue forward. So I'll give you a second to discuss, and then if not, then we'll start with the warm-up. Okay, so let's look at the warm-up question. Is this guy, just a little review of exponent properties, but then kind of applying it with fractions. So pause the video now, give everyone maybe, I'd say, a minute to try these two questions. We'll come back, warm up with these, and then we'll get started with today looking at, again, exponential functions, but now we're not looking at growth, we're looking at growth and decay functions. Okay, so pause the video now, come back after a minute, everyone's had a chance to try these. Okay, welcome back. Let's give them a go. First one says 1/2 to the power of 3. I know, I'll put this as an equals. I know this is the same as doing 1 cubed over 2 cubed. 1 cubed is 1. 1 times 1 times 1. On the bottom, 2 times 2 times 2 is 8. So this is just going to be 1/8. You can even punch it in your calculator and verify. Is a decimal, it might give you 0.125. Second one, again, the 1 was to a power of 1, the 4 was to a power of 1, so this -2 would multiply both of those powers. You'd end up getting a 1 to the -2, and then a 4 to the -2, and what do negative exponents do? Well, they look like they flip what side of the fraction that repeated multiplication is occurring. So this becomes on top a 4 squared, and on bottom a 1 squared. 4 squared is 16, 1 squared is 1, so I end up with 16 divided by 1, and that is just 16. So those are two warm-up questions. They kind of actually help us make some of the tables when we look at decay. So if you would, to start then with today's, would you have out, we're on 7.5, day 2, it should be on writing and graphing exponential decay. So have your note packet out to be able to follow along easily. First part I want to do is just hold a little discussion about the interconnection between growth and decay. So let's take a kind of an easy example. So let's say you have a piece of yarn, and it's a yard, just to make the numbers nice. And we start with that 1 yard piece of yarn. So at stage 0, before I've made any cuts, it's one whole piece and it's a yard long. Then I'm going to cut it in half multiple times. So first time I cut it right down the middle. There are now 2 pieces, and they are each 1/2 yard long. Now what I'm going to do is I'm going to cut each of those into half. So now I'm going to have 4 pieces. Each of them would be 1/4. For each of those pieces, then I'm going to cut them in half. So now I'm going to have 8 pieces. They still need to make a yard total, so each of them must be 1/8 of a yard long. And I do it one last time. Cut each of those 8 pieces in half. I now have 16 pieces, each of them being 1/16 of a yard long. I'm going to write a function for both of these situations. The first one is the number of pieces. So the number of pieces, let's look off. It started with 1, so y equals 1. And what's the pattern here? We're multiplying by 2. So I'm going to multiply by 2 to the power of x. That would be our growth. It's growth because the numbers are getting bigger. We got more and more pieces. Today what we're going to look at specifically are situations like these over here, like the length of each piece. Well, the length of each piece was getting smaller and smaller and smaller. A function for that would be, well, y equals, it still started out at 1. It was still a yard long to start, but its pattern is going to be multiply by a half. Multiply by a half, and it's doing that at each stage. So it started out with 1, and it's multiplying by 1/2 to the power of x, and that is going to be what makes this be a decay. The reason it's decaying is because this guy right here has a special name for exponential functions. It's called the growth factor. There's a little place in your notes where we talk about that later. Because our growth factor is less than 1, we're getting smaller. Over here, our growth factor was bigger than 1, and so the number of pieces was growing. Growth factor bigger than 1, you're going to get growth. Growth factor less than 1, you actually get decay. So that's just a little easy investigation about the interplay between these two. So what we're going to start with is you have to, as a math student, be able to look at a set of data, this is what scientists do too, and determine whether exponential growth or exponential decay is going on, and then write a function for it. So if I look at this guy right here, here's a set of data. What's the pattern going on here? Well, I start at 8, that's my y-intercept, and the pattern here is it's multiplying by half every time. So my function for this would be y equals 8 to start, that's my intercept, and then my pattern is multiply by 1/2. So multiply by 1/2 to the power of x. That would be the equation that models this data. You can go ahead and pick anything you want, like pick x of 2. If you put 2 in here for x, you'd be squaring a half. A half squared is a fourth, and 8 times 1/4 would indeed be 2. So there's just an example of writing an exponential function if you have a decay situation. I want you to give it a go, so you try this one over here, this yo-yo. So pause the video now, give everyone a chance on the whiteboards, take no more than probably a minute. Come back, see how you did it writing your own exponential decay equation. Okay, welcome back. Hopefully you notice the pattern in the table right here is decreasing by powers of, well, multiples of 4. So multiply by a fourth, multiply by a fourth, multiply by a fourth, multiply by a fourth. And so our decay equation is going to be y equals 1. That's our y-intercept to start. And our growth factor here is a fourth. Because our growth factor is less than 1, we are actually decaying. We are getting smaller and smaller over time. So this is the first skill you have to be able to do, is take a set of data, a table, write an equation for it. Okay. Moving on, this part kind of summarizes what I've been talking about, and then here in a second we'll begin to graph our own. So some terms that I've talked about. A is our y-intercept, and I've already talked about what B is. B is our growth factor. And in order to have exponential growth, our growth factor needs to be bigger than 1. Like for example, y equals 2 times 4 to the x. This would be exponential growth. We'd be multiplying by 4 at every stage. That would be growth. So if your growth factor B is greater than 1, we're going to get growth. That's what we looked at yesterday. All of our growth factors were bigger than 1. Sometimes we had 1.5. Even if you have 1.00001, you're still growing by a very small amount. That would be exponential growth. What we're looking at more today are examples of exponential decay. In order to have exponential decay, you need to be somewhere between 0 and 1. Because once you hit 0, you're not growing anymore. You're going to be multiplying by successive groups of 0, and whenever you multiply by 0 once, you're going to end up with 0. So you got to be somewhere between 0 and 1. Another question some of you might think is, well, why can't it be negative? If you actually have a negative growth factor, like -2 or something in here, you could think, well, that would bounce back and forth between being positive or negative depending on your exponent, and we don't look at those cases because there's no real world application for those besides just math curiosity. So in the real world, Exponential decay is only between 0, because then you'd have nothing left, or 1. So you're somewhere between 0 and 1. You could think of like you're only getting back somewhere between 0 or 99.999%. If you get less than 100% back, you're going to be decaying. Like for example, y equals 5 times 3/4. That will be decay because you're only getting back 75% of your prior value each time. So that's a decay situation. I want to show you how Desmos does a really cool job of displaying the difference and similarities between growth and decay. So click on this. I've got it open right here. And you can type this in for yourself. If you go to desmos.com, you can open a new cell and type in the general equation for an exponential. Y equals AB to the power of X. I just use a little caret symbol. And when you do, it'll ask you if you want to add some sliders. You click yes. I've already done it. So here are my sliders right here. I can change A. And you should know as I change A what happens. Well, I'm changing the y-intercept. So here I have a y-intercept of 4. Down here I'd have a y-intercept of -1, -2. Let's get the keyword. There we go. So I can change my y-intercept. That's what A is. It's my initial value. Scientists call it initial value. I can also change B, and B is my growth factor. If I want my exponential to grow faster, move this, I can make my growth factor bigger so it grows more steeply. If I want it to not grow so quickly, I can make it smaller and smaller and smaller, and then something interesting happens when it hits anything less than 1, it becomes decay. If I want it to decay more and more, I make my growth factor smaller and smaller because I don't get back as much then. Like right here, if my growth factor is 0.3, it means I'm only getting back 30% of what I had prior at each stage. Something interesting happened, you might have noted, at 1. When B equals 1, you're not changing. You're just the same as you were before. You are 100%. Imagine if this was like height. If you were 100% of your height next year, you're the exact same height. So B bigger than 1, you're growing. B, your growth factor less than 1, you are decaying. So you can kind of play around with this on your own time. You can even do growth factors with the negative cases. Like this guy right here is a negative, but it's still growth. Bigger than 1, you're still getting more negative. You can also have decay for negatives. So it starts out negative, but then it's decaying because you're getting less and less amount as you get bigger x values. So you can play around on your own time as well. Moving forward though, goal is to eventually graph these things. So here are 2 examples of some exponential equations. Our goal is to graph them. We're going to graph them by making a table. If you want to use a calculator, feel free. These ones are probably simple enough that you don't need a calculator, but for some of the ones on the worksheet, you have some decimals, you might want to use the calculator to make your tables. So let's start off. My y-intercept here is 2, f of x or y is 2, and then my pattern is multiply by 1/2 every time. So in here, my next point, multiply 2 by 1/2, I'm going to be at 1. Then I would be multiply by 1 again, I'm at 1/2. So going forward is multiply by 1/2. Going backward must be the opposite. That'll be multiply by 2. So if I cut something in half, this must have been a 4 over here, and this must have been an 8. So I'm going to graph this guy in blue. My y-intercept is at 0, 2, and then I'm cutting in half. So at 1, I'd be at 1. At 2, I'd be at 1/2. You can even do the next one. At 3, I'd be at 1/4. And then going backwards at -1, I was at, what was it, 4, I think? Yep. And then I can kind of continue on. I'm just going to sketch in here the general pattern though. It looked like this. Another key thing, you cannot hit 0. You are never going to end up with anything less than 0 or 0. You just keep cutting in half. You're going to still have something left. Okay? So there's the first one. I'm going to try the second one. This guy I'm going to do in a red to differentiate. Okay, shoot, this should be -2. 0, -2. And then the pattern here is going to be multiply by 2. So multiply by 2, I'm then going to be at -4. And then I'll be at -8. Going forwards, multiply by 2. You should notice by now this is an example of exponential growth because my growth factor is bigger than 1. Going backwards is the opposite of multiply by 2. It'd be divide by 2. So this would be -1. This would be -1/2. Now I plot my points. 0, -2 was the first one. And then it was 1, -4. That's about as much as I can fit on this guy. At -1, it was at -1, at -2 is at -1/2, and then probably -1/4. It looks like this guy. And this is exponential growth. It's growing. The reason it's growing is because I go left to right. It's getting bigger and bigger and bigger. We always read graphs left to right. So I'm going to zoom out a little bit. It'll look like that. So my blue one is exponential decay. My red one is an example of exponential growth. You should be able to make a table and graph your own exponential functions. Okay. Right here, this isn't in the note packet. I just wanted to show a picture, note the similarities and differences between a couple equations. So here's a table, and I think it's not as beneficial to look at a table. We're going to look at the graphs. So here we go. Thing to notice about all these guys is they're all exponential decay. I know they're all exponential decay because I look at their growth factors, and they actually all have the same exact growth factor, 1/2. They're all getting only 50% of their original value. If I look at this red one, the only difference between the red and the blue is the red started out at 3, and the blue one actually started out at 1. It was 1 times it. That's why it has a y-intercept of 1. This guy starts at 3. They're both decay because they're losing amounts. They're going towards 0 as x gets bigger. And over here, this green one is just negative. It just started out flipped across the x-axis. It started out at -1/3 right here, and it is also decay because it's less than 1 for its growth factor. It's going towards 0 as x goes along. So just kind of showing similarities and differences between graphs based on their y-intercept or their growth factor. Okay, moving along. Just a couple more examples, and I'll have you try one. So these are kind of similar to the ones that you might have in your homework tonight for on the worksheet to practice graphing. So we're kind of going to go a little quicker through this one. Start by making a table. Your y-intercept is at 2. So at 0 you got 2. The pattern is multiply by a fifth. So multiply 2 by a fifth. I'm just going to write it as a fraction. It's 2/5, 0.4 if you want to. Then multiply 2/5 by a fifth. Well, that would be 2/25. If you want it as a fraction, it's 0.08. Okay. Going backward, think about this. If going forward was multiply by a fifth or divide by 5, going backwards would be multiply by 5. So this must have been a 10 and then a 50. Now I'm going to plot as many points as I can. It goes pretty quickly off the graph though because these things grow and decay so quickly. First point was 0, 2. That's my y-intercept right there. Then 1 and 2/5. That's a little bit less than half right there. Then at 2 I'm almost near 0 now. I'm like right there. At -1 I'm all the way up at 10. So this guy decays pretty quickly, and the reason it decays so quickly is because its growth factor is 1/5. 1/5 as a decimal is 0.2. So really what this means is this function is only getting back 20% of its value after each x. What would the domain be? Our domain, our x's are almost always going to be any real number. So for my x's can be any real number for my x's. My range or my y values, the only y's I'm going to get are the positive ones. So my y's have to be bigger than 0. Example of an exponential decay that decays pretty quickly. Second one I want to do is notice this. So if you look at this guy, there's none in the homework like this. I just want to kind of test your guys' knowledge a little bit, push you a little bit because I think you can. This looks almost identical to the one above. It's 2 times 1/5 to the x minus 3. So let's just put 0 in there and see what happens. When I put 0 in for x, I get 1/5 to the 0, and that is 1 because anything to the 0 power is 1. Then I end up with 2 times 1. Let's show the workout since I'm not there. I'm going to put 0 in for x, show what this actually is. 2 to the 1/5 power 0 minus 3. Okay. Anything to the 0 power is 1. So this really becomes 2 times 1 minus 3. 2 times 1 is 2 minus 3 is -1. So, it moved it down. So this is at -1 now. Go ahead, put 1 in for x. Now I'm going to erase all this prior work. I'm going to put 1 in for x. Okay. See what happens. You use the calculator too, but it becomes kind of more apparent when you show your work. So I'm going to put 1 in now for x, filling in a table. So y equals 2 times 1/5 to the 1 minus 3. Well, 1/5 to the 1 is just 1/5 times 2 is 2/5. So this next value is going to be 2/5 minus 3. But notice this. Up top, when x was 1, our answer is 2/5. Now, what I'm going to put in right here is going to be 2/5 minus 3. So what I'm starting to notice here is actually each of these y values are going to be the same as they were in this table up above, just subtract 3. So 2/5 minus 3, 2/5 minus 3 is going to end up giving me like negative 2.6. But the thing I want you to notice more than anything is all it was this guy subtract 3. So I can even fill in this next one. I don't even need to plug in here 2 for x. I just know it's going to end up being 2/25 minus 3, because that's the only difference between this bottom one and the top one, is there's a subtract 3 at the very end, last step. So on your calculator, type in 2 divided by 25. It's the 0.08 and subtract 3. So when I put 2 in there, I know I'm going to get negative 2.92. Now I'm going to fill in this guy. Well, if this guy was 10, when I put negative 1 in, now I'm not going to get 10. I'm going to get 10 minus 3, so there should be 7. When I put negative 2 in for x, go ahead and give it a try if you don't believe me. Put negative 2 in for x and evaluate. You're going to find you get 3 less than 50. You're going to find you get 47. So let's plot those points. So I'm going to plot them. I get a 0, negative 1 y-intercept, so it's going to be right down here now. Then I get 1, negative 2.6, right about there. And then 2, negative 2.92, somewhere like here. Negative 1 up here at 7. And then it doesn't fit. What I want you to notice, though, is what happened. It moved our whole graph down by 3. So now my domain didn't change. My domain, I can still pick any real number for my x's, but my range certainly changed. Because it dropped all these down by 3, now my range isn't y greater than 3. My range is going to be any y value bigger than negative 3, since it dropped everything down by 3. This is called a transformation, and you'll study these a ton in Algebra 2. I want to give you a little preview of it. When you get functions that look just like prior ones, where you just do one change to it, like minus 3, all it does is it'll move your graph up and down, or sometimes left and right. So this is just a preview of something you'll see in Algebra 2. Don't freak out too much about it if you kind of had some trouble following. There's not any questions that I'll ask in the immediate future about it. I just wanted to give you a preview. Okay? What you do need to be able to answer is a question like this. So, on the whiteboard, give this one a go. Make sure you can answer a question like this. This is kind of like the meat and potatoes of today's topic. So pause the video for maybe a minute and a half, 2 minutes, make the table, and then plot the graph on the back side on the whiteboard graphing. And then we'll come back, we'll go over it real quick. Okay, welcome back. Let's fill this in real quick. I know my y-intercept is going to be negative 1, and my pattern is multiply by a third, so then I'll be at negative 1/3 when x is 1. When x is 2, multiply by a third again, I'll be at negative 1/9. If going to the right is multiply by a third or divide by 3, going to the left must be the opposite, which would be multiply by 3. So this must have been a negative 3. This must have been a negative 9 when x was negative 1 and negative 2 respectively. Now I'm going to plot my points real quick. Start down here at 0, negative 1. Then I go to 1, negative 1/3, 2, negative 1/9. These decay really quickly. Negative 1, negative 3, and negative 2, negative 9 doesn't really even fit. So I'll do my best to sketch this. It's going to look something like so. Domain for this guy is going to be any real number for x, and my range is like all the ones we've seen prior. It'd be any y value that's less than 0. No transformations here. Okay, so that's the key skill that you need to be able to take out of today. Similar to yesterday, make a table and graph an exponential decay equation. Very last part, and then the rest of the time will be for you to complete the other worksheet that was stapled to the one yesterday. Be able to look at a data set Determine if it displays exponential behavior. If so, write an exponential equation for it. If it doesn't display exponential behavior, be able to say why not, and maybe even write an equation for it. So let's look at the first one. I look at this guy. What are my patterns for my y's? It looks like, let's go from -4 to -12. It looks like it's multiplied by 3. Multiply by 3, multiply by 3. Yep, this guy's multiplying by 3 every single time from here to here to here to here. That is exponential behavior. When you're multiplying by a constant number, that is going to be exponential. Your y-intercept is -12, so it'll be y equals -12 times 3 to the power of x, because repeated multiplication is exponential. So look at the second one down here. Over here, how do I go from -12 to -6? Well, I would divide by 2, but that pattern doesn't continue, so this is not exponential. What is it? It looks like every single time here you are adding 6, whereas up here we're multiplying by 3. Repeated addition is not exponential. That's actually a linear quality. So this is going to be a linear function. It's actually y equals -6 is your y-intercept, and you're adding 6 for every x. So this will be linear. Very last one. Let's look at it. To go from 1 to 4, multiply by 4. Yeah, it's multiplied by 4 every time. So the pattern from here all the way through is multiplied by 4. That is exponential behavior. And so my equation be y equals 1 times 4 to the x. You'll see textbooks will regularly not write the 1. They'll just write it as y equals 4 to the x. The first two were exponential, or sorry, the first and the third were exponential. They actually were both exponential growth. And then that middle one that we just saw was not exponential, it was linear. So that's another goal, is be able to look at data, assess whether you can do an exponential or a linear to it, because eventually you're going to build a toolbox of different functions. You'll have linear, you'll have quadratic, you'll have exponential, you'll have things called logarithmic functions you'll study in Algebra 2. And a big goal of any mathematician or scientist is to be able to say what type of equation or function models that data. So that's the end of the discussion for today. Rest of your time is just to work on that second worksheet. So it's the one that was stapled out yesterday. It's just the second one for that. So the rest of the time is yours, and then I look forward to seeing you when I get back on Monday. Thank you.